So in our first example with composite functions, we actually didn't talk about the domain. And the reason was that we had two simple functions. I think one was linear, one was quadratic, and their domains were both all real numbers. And so when we composed the functions, we still had a domain of all real numbers. There was just no issue with the domain when that's the case, when they're all real numbers. When we have restricted domains in our original functions, though, the domain of the composite can get a little bit more complicated. So we're going to look at two functions that both have a restricted domain and see how we can handle those. So the f function is the square root of x plus 1, okay? Now, this square root does have a restricted domain. Think about that square root graph, right? It doesn't, all real numbers does not work in that graph. You can't have negatives under the square root. You actually can have 0 under the square root, so the square root of 0 is 0, right? So what we have to do to find the domain here of f is say x plus 1, whatever the stuff under the square root is, should be greater than or equal to 0. Okay, so we can always take the stuff under the square root, set it to greater than or equal to 0. That will tell us our domain. So x should be greater than or equal to -1, right? In interval notation, that's greater than, so -1 bracket to infinity, parenthesis, right? So every number greater than or equal to -1. That makes sense. If you plug in -1, you get the square root of 0. And then if you plug in larger numbers, there's no issue with the square root. Okay, in the g function, let's do that same thing. Let's write that one in pink. 1 over x, we know actually that we cannot have the number 0 in the domain. For the domain for a rational function, remember the denominator cannot equal 0. So in this case, x cannot equal 0. So the domain of this function, if you wrote it in interval notation, would be -infinity to 0 with a parenthesis union with 0 to infinity. Okay, so let's see how that affects our function composition and really hope for the best. So let's do the f of g of x first. Okay, I wrote this since I was writing it. I just wrote it in nested form. This is the way I like to think of it. So f of g of x, the g is the inside function. So in other words, the 1 over x is going into the f function. We're doing the f of 1 over x. So that would be the square root of 1 over x plus 1, right? So notice that in this function, this is the outer function, the f, and the inner function g is in there for x. Okay, so now let's look at that domain. So first of all, this must exist in order to be able to plug it in, right? So we already have a domain restriction that x cannot equal 0. Right? And that is from here. Why did I just write that in blue? Let me write that back in pink, just for consistency, right? This must exist to be able to be plugged in. So we have a restriction of x cannot equal 0. Okay. Then we also still have this restriction of the square root. So we have the square root of 1 over x plus 1, and that has to be greater than or equal to 0. So 1 over x plus 1 must be greater than or equal to 0. Okay, this is a little complicated, but I think it's something that we've done before. We used a sign chart to solve it. So hopefully you won't have anything even quite this difficult, but it's still a good exercise here. So let's see what we can do. Remember that we would want to get a common denominator. So we would want to multiply the 1 by x over x. So we get 1 plus x over x. Our denominator is x, and that is greater than or equal to 0. Okay, so let's make a sign chart. The 0 of the function is x is equal to the numerator there, 1 plus x, so that's -1. And the undefined is x is equal to 0, right, from the denominator. So that's the only things we have to put on this sign chart, -1 and 0, right? So, and remember that the 0 will be undefined, and then the 1, since it's greater than or equal to, we want to include that number. Okay, let's plug in some test points. So let's plug in -2, let's plug in -0.5, and let's plug in 1. Okay, let's do this relatively quickly, but make sure you understand what I'm doing. Okay, so I'm plugging -2, the test point, into this function right here. Okay, so if I put in -2, I'm getting -2, I'll write it down, -2. -2 plus, oh, geez, 1 plus -2, right? 1 plus -2 divided by -2. So that is -1 over -2, which is a positive number, right? So this is positive. Now I'm going to plug in -0.5. If you don't know what I'm doing, you need to go back to the instructions and videos on the solving inequalities, right? This is solving a rational inequality from the last section, last week, week 5. And let's plug in -0.5 for x. And we're going to get, this is positive 0.5 divided by -0.5, so that is a negative number. So this part is negative. And then let's plug in 1. So 1 plus 1 over 1, obviously that's a positive number. Okay, so it looks like we have our answer. I'm going to shade the part of the number line that we want. This is greater than or equal to 0, right? So that's the positives and the zeros. That's here and here. Okay. What a good review of that other section, right? So we're looking for the positives and the zeros. So our answer is -infinity to -1 bracket, and then parenthesis 0 to infinity. That's just the part that was highlighted. So this is the domain. Let's double check that the domain is satisfied, okay? So first of all, the -infinity to -1, right? If we plug in, think about it in this answer function here. If we plug in -1 here, that would be -1 plus 1, which is the square root of 0. See, that's okay. If we plug in down here, right, something larger, let's say like -10, that would be -1/10 plus 1. That's why that's a positive number. So we are good. Now, can we plug in 0? No, right? That's why there's a parenthesis there, because that would still be 1 divided by 0. And then if we plug in numbers larger than 0, though, like let's plug in 2, we would get 1/2 plus 1, which is a positive number, so it's fine. So this is our domain. And like I said, this is probably as hard or harder than it would ever get. So, you know, don't be terrified of this. Let's look at the g of f, because that one is actually slightly easier, I think. So the g of f goes the other direction. Let me pull this. Let's see. What do we want? We're going to go, let's go over to this side, I think. So I can still kind of see both functions. And like I said, I think it's shorter, so I don't think we'll need quite as much space. Cross our fingers, right? So the g of f of, oops, really didn't do those parentheses right, did I? The g of f of x, there we go, means that we're plugging in the f function into the g function. So that's the pink is the outside function and blue is the inside function. So that's the 1 over, and then the blue function is square root x plus 1. Okay, so this is our answer for our function. And then to find our domain, okay, we're going to take a look at, make sure that f exists, right? F has to exist. So So f exists on the domain of f. X is greater than or equal to -1. So -1 to infinity, right? So this is as big as we could get. We can't put more negative numbers in because then f wouldn't exist. All right, then we're going to look at our final function, and we have the 1 over the square root of x plus 1. So really, I can see the -1 to infinity, but if I put -1 into there, look at that. 1 over -1 plus 1 is 1 over the square root of 0, and that is undefined, right? So we cannot include that point that makes that 0. So we're going to do x plus 1 and just do greater than 0. Don't do greater than or equal to because it's in the denominator. So this would be x is greater than -1 is the domain, or parenthesis -1 to infinity. So that's the only difference there. So this one's very close to what we had already done, and like I promised, much easier than the other direction.